All right, now's game time. These are the types of problems your teacher likes to give. Who knows? Maybe on an exam, I'd just tell you, hey, set it up. Just set it up. We'll get it. So here's our area one more time, integrals. But now we're going to use two different regions. So straight from your text, we're going to find areas of polar regions. Consider the circle with a radius equaling to 1 and the cardioid. Telling you it's a freaking cardioid. R is equal to 1 plus cosine of theta. So part A, these get a little bit tricky. Find the area of the region inside the circle and inside the cardioid. And then for part B, we want to find the area of the region inside the circle but outside the cardioid. So I think the first thing we should probably do is just sketch a graph. It doesn't have to be perfect. So a circle with radius 1, let's just draw that one in blue. Circle-ish, huh? And then we're going to want to, so there's our circle, r equals 1. Now, so that would be right here at 1. And then we're going to draw our cardioid in there. But remember, we have a 1 plus cosine. And notice, I'm not giving you, there's nothing here that's super crazy. I'm not giving you like 2 plus 18 cosine of theta or anything. So I just want to think what happens if cosine is 0, just to show something. So when theta is equal to 0, when theta is equal to 0, what would we get, right? This is theta equals 0. We would get that r is equal to 1 plus cosine of 0, which is r is equal to 1 plus 1, r is equal to 2. So our cardioid, it's bigger. So it's going to do a little something like this. I don't know whether I'm being perfect or whether I'm... Yeah, that was pretty bad. Let me try that one more time. I don't know, maybe it goes a little something like this. But there's symmetry to this. So there's a kind of a sketched out graph. Not perfect. Not perfect. But how would we know where those intersections are? How do I know that these are going to connect like this? So all you need to know, minimizing. Maybe I'll just shut up right now. All you need to know. You do need to know where the points of intersection are at. That's the big thing. You got to know where these points of intersection might lie, right here. Now, I'm just claiming that it's at pi over 2 and 3 pi over 2, right? Pi over 2, pi, 3 pi over 2, 0 and 2 pi. Well, you're going to need to do that by step 1. You set them equal to each other and you solve. All right, wasn't this how we did this before? So we subtract over the 1, we subtract over the 1. 0 is equal to cosine of theta, therefore theta is equal to pi over 2 or 3 pi over 2. And that's why we have our points of intersection right here. I cheated. I'm looking at a freaking graph when I'm doing this with you. But now we have a curve sketched out. We're good to go. We're good to go. Now we can start to solve. And we'll get rid of all of this. Now we can start to solve for the area. So for A, I'm actually going to do this because we need to do it twice. Let me copy this thing. Copy. And let me paste it over here. Okay. And let's look at the two different scenarios that we have. So for part A, I'll do that one in blue. We want to find the area of the region inside the circle and inside the cardioid. So it needs to be inside of both. So it's going to be this region here. It's inside both of them, right? Right. It's inside the circle, which is in blue, and it's inside the cardioid, which is in purple. Now let's go to B, and we're going to find the area of the region inside the circle and outside the cardioid. So the circle's in blue, so we don't want anything inside the cardioid. We just want this region here. So now we're thinking, remember when we were doing area between curves, it was above minus below? Now it's outside minus inside. Up top, we're thinking outside squared minus inside. Outside minus inside. All right, now we can go through. We can start our problems, and let's do part A. And symmetry is everything when we're doing this type of problem. How do we do this? Man. So I'm thinking we could probably make our life fairly simple by using symmetry. What should we do here? I got it. Let's look at this. So this is a semicircle on one half of this, right? That's just a semicircle with radius 1. So we know that we have some area is going to be 1/2 r pi r squared. That's part of it, plus, and then we're going to have to do some more stuff. We'll write it in a second. But our radius is equal to 1, so our area is equal to pi over 2 plus. Then we need to find the rest of the region. All right, that little plus some other nonsense. We need to find what's inside of here. That has nothing to do with the frickin' circle. That is just the cardioid. From pi over 2 to pi. And then we'd have to go even further to here. But why would we do that? It's symmetric. Even though my picture doesn't look like it's symmetric, it's frickin' symmetric. So we could say that this is actually just 2 times the integral from pi over 2 to pi of the cardioid. And what was the cardioid? 1 plus cosine of theta. So we go, oh, okay, so it's 1/2 squared r 1 plus cosine of theta. D theta. Let's clean it up. Let's drop it down. 2 times 1/2. Oh, sweet. Pi over 2 to pi. And now we just have to square up our 1 plus cosine of theta. And that's 1 plus 2 cosine of theta plus cosine squared of theta. And I'm just using old distributing properties. And now we got to solve this whole thing out. And oh, look what happens again. We got to use that freaking reduction formula one more time. So let's clean it and go. All right, got our pi over 2 plus our integral from pi over 2 to pi of 1 plus 2 cosines of theta. And we're just going to write this thing in. Cosine squared of theta is equal to 1 plus cosine of 2 theta all over 2, but I'd rather write it this way. And I'm going to do a lot of cheating so we can get through both problems in under about 15 minutes. No, thank you. I'm going to take this 1/2 and this 1 and I'll put it together and call it 3/2. If you don't mind. Just save some time. Bring that back over. Okay. Now we can start doing a little bit of calculus, huh? I know everybody's having fun right now. I know you're all having a good time, aren't you? So we got 3/2 theta plus 2 sine of theta. And this is also going to be a plus. We got a cosine, so we're going to have sine of our 2 theta. And are we going to multiply or are we going to divide by 2? We're going to divide, so it's over 4. And we're going to evaluate this from pi over 2 to pi, which is pretty convenient because, well, sines of pi is equal 0, sines of 2 pi is equal 0, so we have our pi over 2, which has nothing to do with any of this. So we have 3/2 pi plus 2 times sine of pi plus sine of 2 pi. These are all zeros, by the way, except for the first term. And then we're going to do minus, so all our terms, I'm going to throw a minus on us, so I don't have to use another freaking parenthesis. Minus 3 over 2, pi over 2, minus 2 times sine of pi over 2, 1. Plus sine of 2 times pi over 2, that's just pi, that's 0. Oops. I said, I'm going to write a freaking minus everywhere, so we don't have to write. I'm so silly. All right, so what do we have? We have pi over 2 plus, well, that's 3 pi over 2. That's 0. That's 0. That's 0. So then we have, So those first two went away. Now we got to deal with minus 3 pi over 4. Minus 2 times 1. And oh, there it is. So we have what? 2 pi or 8 pi over 4 minus 3 pi over 4 minus 2. What is that? 5 pi over 4 minus 2? Oh my goodness. Well, congratulations. We've done one problem. We haven't even done part B yet. But I'm going to fly through part B. All right, let's do part B now. I'm not going to explain a lot of steps on this. So we look at part B. We want to find the area outside the cardioid, inside the circle. So we're going to use the same logic that we had before with using symmetry. I want to find it from 0 to pi over 2. Or from pi over 2 to pi. Good golly, I can't speak. And then we're going to multiply it by 2. But now we're going to finally use our formula. We're going to say the area is going to be, and let's say it's 2 times the integral from pi over 2 to pi. Also, if you went from pi over 2 to 3 pi over 2, you'd end up having an answer that's not true. So you got to use your symmetries here. And what's the outside function? The outside function is the frickin' circle. As we look in there, we need to make sure to find the area of that circle, but we got to subtract out this area here. So we're going to do our outside minus our inside. So it's going to be our 1 squared, that's the circle, see, r equals 1. Minus our cardioid squared. So what is that? 1 plus cosine of theta. All squared d theta. Now we have 2 times the integral of pi over 2 to pi of 1 minus 2 cosines of theta minus cosine squared of theta d theta, jumping these steps. So clearly 1 minus 1 is gone. And we can just bring this back over, and we have negative 2 cosine of theta minus cosine squared of theta. And the integral works like this. It's 2 minus pi over 4. Sorry, I'm just jumping it. You've integrated sines and cosines enough. I don't think you need my help at this point. There it is. We would just solve it, and we would get this freaking value to pop out of it by using, again, we'd have to use our reduction formula. We'd have to work through, and we need to get our answer out of it. This is our game, our inside and our outside. A little tricky. A little tricky. All right, so I think we're going to do one more small problem. We'll do a short one next, and then we're going to move into... Actually, we're going to do a couple things here. Yeah, and then we'll move on into finding the lengths of curves, and we will be done with Chapter 12. Hooray! All right, I'll see you there.